Hello everyone, this is Maithili, working as Assistant Professor in Department of Chemistry, St.Josephs Arts and Science College for Women, Hosur. We will see about first Henderson-Hasselbalch equation. Describes the derivation of pH as a measure of acidity in biological and chemical system. The equation is also useful for estimating pH of a buffer solution. It is widely used to calculate the isoelectric point of proteins at which protein either accept or yield proton. This equation is mainly used to calculate the pH of the solution. The Henderson-Hasselbalch equation for acid is pH equal to pKa plus log A minus divided by HA concentration. Here, pK equal to minus log Ka, where Ka is the acid dissociation constant, that is pK equal to minus log concentration of H3O plus concentration of A minus divided by concentration of HA. For the non-specific Bronsted acid-base reaction, HA plus H2O gives A minus plus H3O plus. Here HA is acid, that A minus plus H3O plus is conjugate base. The Henderson-Hasselbalch equation for base is POH. Acid means pH, base means POH. Here POH equal to pKb. Acid means pKa, it will come. Base means pKb, it will come. So pKb plus log BH concentration divided by concentration of B, where BH plus denotes the conjugate acid of corresponding base B. B plus H2O gives BH plus OH minus. Here B is the base, BH is the conjugate acid. Next, Henderson wrote on the equation in 1908, described the use of carbonic acid as a buffer solution. Carl Albert Hasselbalch later expressed the formula in logarithmic terms, resulting in the Henderson-Hasselbalch equation. Hasselbalch equation was using the formulas to study metabolic acidosis. Derivation. According to Bronsted-Lowry theory of acid and bases, the acid of HA is capable of donating proton H plus and is capable of accepting a proton. After the acid HA has lost its proton, it is said to exist as the conjugate base A minus. Similarly, a Bronsted base is said to exist the conjugate acid BH plus. We will see about the salt hydrolysis. Salt hydrolysis is defined as the reaction of cation or anion of salt with water to produce either acidic or basic solution. In salt solution, its water is mixed to give salt solution. It may be either acidic or basic. On the basis of relative strength of acid and base produced due to hydrolysis, salt are classified into four classes. Salt of strong acid and strong base, NaCl, NaNO3, Na2SO4, KCl, KNO3, KTSO4, etc. are the example of salt of strong acid and strong base. Being this salt as strong electrolyte, they give cation and anion when dissolved in water. These ions do not hydrolyze. That is, these ions don't interact with water. Consequently, there is no change in concentration of H plus and OH minus ions in the solution. Hence, the resulting solution is neutral. Example, in broad, hence it can be generalized that the salts of strong acid and strong bases don't undergo hydrolysis and the resulting solution is neutral. We will see salt of weak acid and strong base. Sodium acetate, sodium bicarbonate, potassium carbonate are the example of salt of weak acid and strong base. And treating these salts with water produce weak acid and strong base. Example in broad, acid produce OH minus ions. The solution of such salt is alkaline in nature. Next we will see salt of strong acid and weak base. Ammonium chloride, copper sulfate, ammonium nitrate, aluminum chloride, calcium chloride, ferric chloride, etc. are the examples of salt of strong acid and weak base. And treating these salts with water produces strong acid and weak base. Example in broad, acid produce H plus ion, and solution of such a salt is acidic in nature. Next, salt of weak acid and weak base. Ammonium carbonate, aluminum phosphate, ammonium acetate are the example of weak acid and weak base. And treating the salts with water produces parent weak acid and weak base. Thus, it involves both cation and anionic hydrolysis. The resulting solution may neutral or slightly acidic or basic depending upon the relative degree of ionization of the weak acid and the weak base produced. Next, solubility product. A salt dissolves in aqueous medium and at a point the dissolution stops and the salt of ion will be equilibrium. This stage is called saturation. For example, silver chloride dissolved in water. At the saturation point, silver chloride gives silver plus chloride in aqueous medium. Factors that affect the solubility. Temperature. Solubility generally increases with the temperature. Common ion effect also reduces solubility. pH of solution. pH affects the solubility of ionic compounds. Formation of complex ion. The formation of complex ion increases solubility. These are the four factors affect the solubility: temperature, common ion, pH solution, formation of complex ion. Solubility product constant is Ksp. Most salt dissociated into ions when they dissolve. For example, barium sulfate gives barium 2 plus plus SO4 2 minus. The equilibrium system may be described by the mass of action expression Ksp equal to Ba2 plus SO4 divided by SO4 minus. Application of solubility product. The salting out of soap is the one of the most important application for the solubility product. As the name implies, soap is the sodium salt of very fatty acidic compound. Adding concentration solution of sodium chloride and cashew seeds to precipitate out of the solution. Pattern of solubility product. The solubility product is a kind of equilibrium constant at its value depends upon temperature. Ksp usually increases with the increase in temperature due to increased solubility. Solubility is defined as a property of substances called solute to get dissolved in a solvent in order the form of solution. Thank you.